Yeah. So very first model that we have taken is PN junction diode. This is not new to you because you already have gone through these PN junction diodes or the semiconductors in PUC or maybe in high school itself. Okay, we'll be just trying to get some sort of refresher course on this. Okay, so you might have forgotten what is p type semiconductor, n type semiconductor. If you remember, it's well and good. Okay, if you don't, that is what this class we are doing. Fine. So let's take the introduction to semiconductors. Let's get into the PN junction diode after this. Fine. uh, yeah. Now, what are semiconductors? See, there are, this is also material. This is also material, okay? Solid material. Fine. And if you take semiconductor, what are the other types of materials you can think of? There are conductors, there are insulators, and these are semiconductors. What are semiconductors then? See here, semiconductor material is that whose electrical conductivity falls in between that of conductor and insulator. What is a conductor? If you take any conducting material, for example, they have said metallic copper you can take, okay, or iron you can take. Fine. So that is conductor. What is an insulator? The one which would not conduct is called insulator. You can take plastic, you can take fiber, you can take glass. They're all insulators. So what is semiconductor? Semiconductor is a material whose conductivity falls in between that of conductor and insulator. It's neither conductor nor insulator. Okay. So that is how the conductivity of semiconductor is. It's not as good as a conductor's conductivity, or not as bad as insulator's conductivity. Okay, so that is a semiconductor. That's why the name semiconductor. Okay, now there could be some mischievous minds among you which may think this: if its conductivity falls in between that of conductor and insulator, why it should be called semiconductor? Why it cannot be called semi-insulator? Right? The name says semiconductor, but its conductivity falls in between conductor and insulator. Why it should not be called as semi-insulator? Anybody would like to go on with that? Just a thought. Just a thought. Why it should not be called a semi-insulator? Why that importance to conductor here?
Most probably it acts as a conductor.
No, not like that. We can make it insulator also. It will conduct. We can make it not conduct also. In that sense, we can bring it near to insulator also. We can take it near to conductor as well as we can bring it near to insulator. Maybe you're a little near to what I expected. That's fine. Anybody would like to approach that particular question? Why it's not semi? It's not called semi insulator, whereas it could have been called so. Yeah, let me tell you that the property that we are interested in is, yes, yes, go on. No, just a sec. Your audio. Just a minute. Just a minute. Your audio is not clear. If somebody has, if you have switched on your video, just switch off your video because it will take extra bandwidth. So let's stick only to the audio. Okay with that? So if anybody has switched on the video, just take that off. We'll be keeping our audio on, and we'll keep our audio on whenever it is required. Otherwise, it is unnecessary usage of bandwidth, and it will make our speed slow. Understand that? So you can, when you're talking, bring your audio on. Your video is always off, okay, and your audio is on whenever you are talking. Otherwise, you will keep it mute. Yeah, everybody mute your audio, and those who are talking can talk by unmuting the audio. Yeah, somebody was talking. Yeah, go on.
Maybe because of its usage, we use it Like we use it as transistor, diodes, and all, which is based on its property of conductivity.
Lovely. That is what I expected. That's good. Okay. So now, since the interest is on the conducting property of the material, okay, we are not interested in insulating property of the material. See, insulation is equally important. Insulation, what we are talking about, is equally important. Okay, but here when it comes to semiconductor materials, the property that we are interested in is the conducting property of the material. That's why the name semiconductor. Okay, now that means I can vary the conductivity of this. Okay, so how I can do that? Let's see. Now its conducting properties may be altered in useful ways by introducing impurities. We call them as impurities. Okay, so introducing the impurities in the materials are also called as doping. Everybody understand this? This doping is the word that they use in electronics. Okay, for adding the impurities to the material. Understand that? So which material we add impurities to? Suppose we say semiconductor. Okay, the conducting properties of the semiconductor can be varied by adding the impurities to it. Okay, and that process of adding impurities is called as doping. Okay, and where do we add it? We add it to a crystal structure. See, semiconductor or any material for that matter comes in a crystal structure because they are tightly bound. Okay, this crystal structure is something that is bonding the atoms of the material together. Understand? That is why it is called as crystal structure or lattice structure. Also sometimes we call it as. So understand, the process of adding impurities is called doping, and by doing so we can change the conducting property of the material. Understand that? Now, yeah, the conductivity of silicon is increased by adding a small amount. Now suddenly the word silicon came. Okay, now can you tell me which are the semiconductor materials? One is silicon. Which are the other semiconductor materials? You can unmute and you can go on.
Germanium.
We have known germanium, we have known gallium arsenide. Okay, these three, silicon, germanium, gallium arsenide, are the most widely used ones. Okay, they are most widely used semiconductors. Now they in themselves have some differences which we will understand as the time goes. Okay, now as of now, understand there are many semiconductor materials, but among those the popular ones are silicon, okay, then germanium, then gallium arsenide. Fine. Now how can you change the conductivity of the silicon? We said we add impurities. How much impurity you are going to add is the question. Okay, so if there are 50% of silicon atom, will you add another 50% of impurity to it? No. See the amount of impurity that we add. Okay, see what is the amount of impurity. So if there are 10 power 8 atoms of silicon, if there are 10 power 8 atoms of silicon, okay, the impurity is added in the order of 1 in 10 power 8. That means if you add impurity, okay, that impurity should be added as one impurity atom per 10 power 8 atoms of silicon. See, that is so small impurity we add to change its conducting properties. Understand it? It's very small amount of impurity that we go for adding to it. Everybody should understand that. Okay, and now when it comes to adding impurity, there are different types of impurities. For example, there is something called as pentavalent impurity. Everybody should be able to see the pointer that I am moving on the screen. Okay, so there are two types of impurities. One is pentavalent impurity, the other one is trivalent impurity. What are the examples of pentavalent impurities? This is antimony, phosphorus, arsenic are pentavalent impurities. Which are trivalent impurities? Boron, gallium, indium. They are all trivalent impurities. So these are pentavalent and trivalent impurities which we add to semiconductor, okay, to vary the conductivity of the material. Now Suppose if we have not doped the semiconductor, that semiconductor is called what? Question to you. Suppose we have not doped the semiconductor. Okay, it's silicon. We're not adding any impurity to that. We're not either adding the silicon or pentavalent or trivalent impurities. So what is that semiconductor called? Anybody? Do you remember?
Impure semiconductors.
No.
Extrinsic
Intrinsic.
semiconductor.
It's not impure. See, if we add impurity, it becomes impure. If we don't add impurity, it's pure form. And that pure form, somebody told, very good, it's called as intrinsic semiconductor. So what are intrinsic semiconductor? Intrinsic semiconductors are those to which we have not added any impurity, whether it is pentavalent impurity or trivalent impurity. We have not added anything. It's a semiconductor which is in its pure form. Okay, and that is what is called intrinsic semiconductor. Get that point? Now, what is that intrinsic semiconductor? What would be the state of its conductivity? Okay, all that we will see later on. But as of now, you understand there is a semiconductor. If we don't add impurities, it's called as pure semiconductor or intrinsic semiconductor. And after adding the impurity to it, it becomes impure. We don't call it impure, but we call it as extrinsic semiconductor. Understand that? Now, that is when we come across the extrinsic semiconductor here. The process is known as doping, and the resulting semiconductor are known as doped or extrinsic semiconductor. We don't use the word impure. We use pure and intrinsic. Here we use doped or extrinsic semiconductor. So which are the examples of extrinsic semiconductors? Anybody? In silicon, when silicon becomes extrinsic silicon, okay, so that silicon can be called as which type of semiconductor? Anybody? There is a silicon which is in its purest form. I add impurity to it. After adding impurity, it becomes extrinsic. In extrinsic, what all do we know? When it becomes
P-type.
exactly, it is P-type
P-type semiconductor.
or N-type. So when it would become P-type, it would become P-type semiconductor when it is doped with free holes. Free holes means what? I'll be coming to that. See, you will have P-type semiconductor when you add trivalent impurity to the semiconductor. You will have N-type material when you add what? Pentavalent impurity to the semiconductor. Understand that? So this is the small introduction that I wanted to give. Okay, understand? I'm not going to show these PPTs to you throughout this semester. Okay, so showing these PPTs may take less time, but when it comes to focusing, one person would lose the focus as if I go on changing the slides like this. So what I have planned is this. Okay, so what I have done now is I've been using Zoom software. Okay, and in that I'm sharing the PPT slides. Okay, now what I'll do is this. I'll stop sharing this and I'll take a new share. Okay, what is that? I'll just talk about that. Yeah, share. And what is that I'm trying to share is this. Yeah. Have you heard about OneNote? Anybody? Have you heard about OneNote document? You know your office documents, right? Microsoft Office documents in your laptop or in your personal computer. Yes or no?
Yes, sir.
You have known Word, you have known PPT, you have known Excel. Okay. So these are all Word documents. So another Word document is the OneNote document. So this is OneNote document. What I'm displaying to you is OneNote document. Okay. This OneNote document is used to write using electronic pen. Everybody understand that? For example, see, this is the page. This is like the whiteboard to you. Okay. So on this I can write. See here. On this I can write. Yeah. say I can select colors here. Okay, I can type. If I type, it looks like what you've been seeing now. Okay, these are the same points which I have explained you just now. Okay, now I'll be trying to write something and explain the same in more depth. Get that point? Now, when will you have p-type impurities? When will you have p-type material? Just a minute. Just a minute. You see here, we will see what is p-type material. Okay, and also we will see what is n-type material. Okay, now you should understand when do we get this p-type and when do we get this n-type. Fine. In p-type material, okay, which impurity needs to be added? Okay, we need to add
Trivalent impurities.
trivalent impurity. Very good. Okay, now if you take the n-type material, we need to add pentavalent. So what does this mean? Adding the trivalent and pentavalent impurities. We shall see that now. Okay. Now, suppose, see here, everybody, I'll be writing the lattice structure now. Everybody understand this. You might have seen this in many, this is what I'm writing is one atom now. Okay. These are all atoms of semiconductor. Any material for that matter will have atoms like this. Fine. Now each atom is bonded with the neighboring atom through something called as the covalent bonds. What I'm writing is the bonds, okay, which is holding the atoms tightly together. Get this point? So what I'm writing is all the lattice structure. This is called as lattice structure, and the bonds are called as covalent bonds. Fine. So this is how the structure looks like. Fine. Now. So there'll again be the neighboring atoms like this. Okay. So which will have bonding with this. Okay. On the other side also you'll have this. Fine. Now here also you'll have. Now let me show you how an intrinsic semiconductor looks like in this lattice structure. Everybody. Now say you have taken silicon semiconductor. Okay. Silicon semiconductor we have taken. What is the valence number of valence electrons in silicon? Anybody? Anybody? The number of valence electrons?
4.
4.
Four.
So that's why it is called as tetravalent. Understand? Trivalent means the valence electrons are 3. Pentavalent means the valence electrons are 5. Silicon, it is called as tetravalent because it is 4 electrons. So see how it looks like now. If it is 4 means it will have 4 electrons like this. Okay. So each electron is bonded. See, these are 4 electrons of silicon. This is silicon atom means. Okay. These 4. See here. This one, this one, this one, and this one. They are 4 electrons. Okay. And each electron of one silicon atom is bonded with another electron of neighboring atom, neighboring silicon atom. Understand this? Okay. These are all silicon atoms. So each silicon of each one electron of silicon will have bonding with another electron of neighboring silicon. So this is how the lattice structure looks like. Everybody. I don't say it is exactly like this. Okay, so this is just a depiction to have a fair idea regarding how the lattice structure would be. Now, can you just tell me, let me just check you with the idea of electron and hole. What's an electron and what's a hole? Can anybody give me what you know about these two current carriers? They are called as current carriers. Electrons and holes are called as current carriers. What do you know about them?
Electrons are negative, holes are positive.
Electrons are negative charge carriers, we should say. Carriers, they are charge carriers. Electrons are negative charge carriers, okay, whereas holes are positive charge carriers. Get that point? Now, do you think both electrons and holes move? Anybody?
Yes,
Electrons
sir.
moves, but holes doesn't.
Holes don't move, but electrons do. Can you elaborate that answer on why? No, whoever it is, that's correct. If you say electrons move and holes don't, that's correct. Actually, practically, that's true. But what makes you say so? Try. Should you may be wrong. That's fine, but that is how one person, one would rather learn better. Go on. What made you say electrons move and holes don't? You're correct. Can you elaborate on that? Anybody? Okay.
In the presence of electric field,
In the presence of electric field, the electrons move.
electron
Electrons move. So don't you think the holes move?
it moves in opposite direction.
Holes move in opposite direction. Okay, that is how we have been taught. No problem, exactly fine. That is how we have been taught. Even when I was doing my engineering or when I was doing my schooling or PU, this is what was taught. Electrons move in one direction and holes move in the opposite direction. That's fine. Okay, so as far as you are saying, what is that is, yeah. See here, electrons move in x direction means, so this is positive x direction, okay, then holes move in what, this negative x direction. This is what has been taught. Now understand the difference. This is fine as far as the explanation is concerned. Now we are going one step deeper. Everybody should listen to this, or anybody would like to say some more on this, about this statement. If electron is moving in this direction, that is positive x direction, holes would be moving in negative x direction. Has anybody got to say anything about these two statements? Nobody? You all agree with this? Fine. If you, this is what we understand. But just one more thing that you understand is this. Now understand this. Okay, see here. Holes are represented by a circle like this. Okay, and electron is represented by a dot like this. There is somebody. You should be watchful on your audio. Bhavana, BU.
ರೋಮಲ್ಲಿ ಹೋಗಿ ಹೊಡಿ ಹಿಂಗ್ ಹೋಗ್ಬೇಕಂತ ಸಾರಿ
Bhavana.
ಹಂಗ್ ಹೋಗ್ಬೇಕು ರೋಮಲ್ಲಿ ಹೋಗಿ ಪಾಕೆಟ್ ಟಿವಿ ಅಂತ ಹೊಡೆದ್ರೆ ಡೌನ್ಲೋಡ್ ಅಂತ ಬರುತ್ತೆ ಫ್ಲಾಶ್ ಇರ್ತಿದೆ ಅದು ಆಮೇಲೆ ಸಿಗ್ಲಾ
Bhavana, can you mute? I'm having problems with my. Yeah. Yeah, everybody speak, yeah. Yeah. the hole looks like this. Fine. The electron looks like this. Understand that? Now, what I'm trying to tell you is, everybody just understand this, very important stuff. This hole is a vacancy. Everybody should understand this. Hole is a vacancy. Okay. Or you can compare this to a chair, which is free. Bhavana is eating something and I'm not able to mute her. Yeah. So we can say this is a chair which is free. Okay. This is a chair, vacancy. Vacancy for whom? Vacancy for electrons. Okay. Say if this is a chair and if electron comes and sits on this. Okay. So what it will look like? It will look like a chair which is not vacant. That is a electron and hole pair. Okay. When an electron sits on the hole, it's called electron hole pair. Okay. Or we can call them as recombination of electrons and holes. Understand this. It is called as recombination of electrons and holes. And what would happen when they recombine? What would happen when they recombine? They'll not be free. Everybody understand this? Again, I'll tell you what is a hole and what is an electron I'm talking about. Hole is a vacancy for electron, which can accommodate electron. Okay. When a hole accommodates an electron, okay, electron will not be moving freely. It would go and sit in a chair. And when it sits in a chair, it won't move freely. Okay. So the conduction is not possible when a hole and an electron recombine. Everybody understand this point? I'll give it a try again. Everybody understand? Hole is a chair, electron is the carrier. When this electron comes and sits on this chair, okay, so this was earlier free electron. Now the electron is not free. Everybody understand this? This is hole electron pair. This is free electron came and sat on a hole because it was vacant for sitting. So it came and sat on that. Understand? So when the electron is not sitting on the hole or sitting on the chair, for example, it is free. When it is free, it is contributing for the current. When it is not free, it is not contributing for the current. So when it would contribute for the current, it would contribute for the current when the electron is freely moving. When it would not contribute for the current, it would not contribute for the current when it is sitting on the hole, when it gets recombined with the hole. Everybody is okay with that? Okay. Now, so what we need to do is, why these electrons would go and sit on the hole there? Because hole is a positive charged thing or element, we can say, and this electron is the negative charged carrier. What's happening between them? There is an attraction. Okay, there is an attraction between the positive and negative charge. So that's why they attract. So when they attract, what would happen? This electron would go and sit on the hole. When it does that, the free electron which was moving freely earlier and was contributing for the current is now fixed and sitting on the hole. It is not free. And when it is not free, it is not contributing for the current. Okay. And let me talk to you regarding the electron movement and hole movement that we talk about. See here, everybody. So let's say there are some holes like this. There are some holes like this. Now say we have one electron here. We have electron sitting on this. Like this. Suppose we say we have electron. Okay. And there is a vacancy here. There is a vacancy here. Everybody should understand this. Very interesting stuff. There is a vacancy. Fine. Now, when there is a vacancy for this particular electron, what would happen to this? What would happen to this? This electron, what it would do? It would, this electron, since there is a vacancy, these are all free electrons, let's say. Or say they are electrons sitting on the holes. Nobody is free here. Let me just tell you again. Nobody is free here. Okay, they're all the electrons sitting on the hole. Now, what would happen is, since there is a hole here, this electron moves from this position to this position. Okay, this electron, because there is a hole here, moves from this position to this position. So when this electron leaves this, what? Leaves this place, what is remaining there? Hole is remaining. Everybody understand that? Hole is remaining. Now, because of this hole, what would this electron do? This electron would move here. When this electron moves in that place of electron, what happened? Another hole is created. Understand that? And since there is a hole created, what would happen to this electron? What would happen to this electron? This electron would move and sit there. So when this electron moves in that place, you have another hole created. Understand? So because of that hole created, what's happening to the electron? It's moving there again. When this moves, again a hole is created. Okay, so when that hole is created, this electron moves there. So this is what is happening. Now what is happening here is, everybody just see here, I'll depict it again. So these are all electrons, and there is a hole here. Is everybody okay with that? Now, because of this electron movement here, so the scenario became this. Okay, and because of this electron moving here, the scenario became this. Now what's happening? For every electron movement, we say that hole is moving to the right. Yes or no? But do you think the hole is really moving? Can anybody comment on that? Do you think the
No,
hole
sir.
is really moving?
No, no.
No.
No,
What's happening rather?
no, sir.
It is just looking like it is moving.
Electrons.
Electrons are moving because there is vacancy. Okay, because of that electron movement, when the electron moves from one place to the other place, the electron which moves from one place, the place which it is leaving is a hole. Okay, the place which it goes and sits is again a hole, but that's a combination of hole and electron. Understand that? So this is what is happening. So electron is moving in one direction, means it seems like the holes are moving in opposite direction. It just seems like. So see, there is a difference between saying it moves and it seems like moving. Understand that? I say the electron is moving from one place to another place because there is vacancy. The vacancy is hole. Okay, when electron moves from one place to another place, the place which it leaves, okay, it creates another vacancy, that is again a hole. Again the next electron, what it does, it moves from one place to another place. So again, it leaves back a hole. So the whole movement is like this. The whole movement seems like it is moving in this direction, whereas electron seems like it is moving in this direction. But actually, only electron is moving, but holes are not. Holes just seem like they are moving in opposite direction to that of the direction of flow of electron. It is just this. Everybody is okay with this point now? Okay. Now, I was telling you the free electrons. Now tell me, anybody, do you think the free electron is sitting or it is moving around?
It's keep moving.
It will keep moving. Has it got the friendship with a hole? That means, is it in combination with the hole when it is moving? Is it combined with the hole when
No,
it is
sir.
moving?
No, sir.
No. So when it is moving, it is free electron. Understand that? When it is not moving, it is combined with the hole. When it is not moving, it is combined with the hole. So that's why we say, maybe you have heard about this explanation. When an electron and a hole combine, they disappear, they say. It's not disappearing. It's becoming immobile. Earlier they were moving around. Okay, now electron has got a very comfortable seat to sit on. So when it sits, it is not free, and when it is not free, it is not the current. It is not contributing for the current. Rather, when it is moving, it contributes for the current. Okay, so this is what I wanted to give you regarding the electrons and holes. Which charge carriers move, electrons move, but the holes move in opposite direction, or we say that just for the explanation sake. Now you're all engineers or going to be engineers, the would be engineers we call. Okay, so if somebody asks you, do you think the holes move as the electrons do? You should say no, they just seem like they are moving. They just seem like they are moving, but actually it's the movement of electrons which results in the current. Fine. Now let's come back to this particular lattice structure with this understanding. Now everybody listen here. In this lattice structure, every electron, see this electron is in within this bond, right? Everybody see this? So this bond, what I've seen, all the electrons are within that. So when I say the electrons are in the covalent bond, they are sitting on the hole. Everybody understand this point? So when I say the electrons are there within the covalent bonds, means it is the hole and electron pair which are sitting there, or which are recombined. Fine. Now you should tell me, if I say all the electrons are stationary electrons which are bonded with each other, okay, and they are not moving. Let me tell you, they are not moving. Okay, and if I say there are some 1,000 electrons sitting in the covalent bonds, can you tell me how many holes are present there? There are no free electrons at all. All the 1,000 electrons are in the lattice structure. Can you tell me the number of holes there? Anybody?
1,000.
1,000. Beautiful. Why?
1,000.
There are 1,000 electrons not moving, means they're all sitting. Just for the explanation sake,
On the holes.
on the holes. Very good. They are sitting on the holes, which is a vacancy. Okay, so there are 1,000. For example, I'm saying if there are 1,000 electrons sitting, means they are sitting on holes. Means what is the understanding there? There are 1,000 electrons sitting on 1,000 holes. That means the number of electrons are equal to number of holes. Get that point? And when the number of electrons are equal to number of holes, that is when we call the material as intrinsic material. Everybody understand that point? So what is an intrinsic material? Intrinsic material is one wherein we have number of electrons equal to number of holes. Number of electrons equal to number of holes. Understand that? That is why we call it as intrinsic, and intrinsic in intrinsic electron there is no current flow because all are happily sitting. Understand that? So number of electrons are equal to number of holes, and that is why we call it as pure semiconductor. If you want to have the addition of impurity, that is when we'll be having creation of electrons or creation of holes there. Get that point? Everybody understand what is intrinsic semiconductor now? Okay, now we will stop this session.